The pursuit of maximum velocity in competitive FPV drone racing demands more than powerful hardware. It requires precise mastery over how thrust, drag, mass, and control authority interact when every millisecond and every gram determines whether the aircraft stays locked on trajectory or devolves into violent oscillation. Drones that reach exceptional speeds frequently lose control, not from insufficient power, but because minor mechanical imbalances, aerodynamic inefficiencies, or electronic response lags become catastrophically amplified the instant throttle rises and momentum builds. At higher velocities, the opposing aerodynamic force grows with the square of speed. Doubling forward velocity therefore quadruples drag, forcing the propellers to deliver far more thrust simply to maintain or increase pace. Simultaneously, the aircraft carries greater kinetic energy. So any small deviation in attitude or any external disturbance requires stronger and faster corrective thrust vectors to restore the desired path. Without sufficient reserve thrust and without a control loop that can apply those corrections cleanly, the drone either under-rotates through corners, overshoots gates, or enters growing oscillations that exhaust battery and pilot alike. The path to higher speed without surrendering control therefore rests on three tightly coupled foundations: delivering efficient thrust across the entire throttle range, stripping away every unnecessary gram and square centimeter of frontal area, and configuring the electronic control system so that it remains accurate and responsive even when motor RPM and airspeed are at their peaks. Begin with the propulsion chain. Motor, electronic speed controller, battery, and propeller must function as a single matched system rather than isolated upgrades. A motor whose kV rating is too high for the chosen cell count will spin the propeller beyond its efficient operating range, wasting energy as heat and turbulence while producing excess torque that twists the frame. Conversely, an overly low kV motor on the same voltage may never reach the RPM needed for competitive top speed. The correct pairing emerges only through measurement. Static thrust tests on a calibrated stand combined with in-flight observation of how quickly the aircraft accelerates and how cleanly it holds speed once the target velocity is reached. When the combination is right, the motors deliver strong thrust even at partial throttle, preserving headroom for attitude corrections during turns and recoveries. Propeller selection directly governs both the conversion of motor RPM into forward thrust and the rotational inertia that affects control response. Larger diameter or higher pitch blades move more air and therefore generate more thrust at a given RPM, yet they also increase drag and require more torque to accelerate or decelerate. Lightweight, stiff blades reduce the energy wasted in flexing and the vibration that flexing creates. Once chosen, every propeller must be individually balanced. Even a few milligrams of imbalance at the tip generates a centrifugal force that grows with the square of RPM. At racing speeds, this force excites frame resonances and injects periodic noise into the gyro, causing the flight controller to fight phantom motion instead of real attitude errors. Balancing removes that primary vibration source before any electronic filtering is applied. Battery performance under load determines whether the thrust remains consistent when it is needed most. Voltage sag under high current draw lowers the voltage available to the motors exactly during hard acceleration or sustained high-speed sections, reducing both peak thrust and the margin available for control corrections. Batteries with high continuous discharge ratings and low internal resistance maintain voltage better, but they must still be weighed against the mass penalty. Positioning the battery so the center of gravity sits near the geometric center of the motors, often slightly forward for racing, further improves handling by aligning the aircraft's natural pitch tendency with the direction of primary flight. Structural stiffness and aerodynamic cleanliness multiply the effectiveness of every thrust improvement. A frame that flexes under motor torque introduces mechanical delay between commanded thrust and actual airframe response. That delay forces the flight controller to apply larger corrections, which can push the system toward oscillation. Rigid carbon construction with well-supported motor mounts transmits commands instantly and reduces the amplitude of any vibration that does occur. Wire routing that keeps leads inside the frame or along the arms, compact component placement, and minimal protrusions all shrink frontal area and eliminate turbulence that would otherwise increase drag. Even small changes compound. Removing unnecessary hardware, shortening leads, and using low-profile antennas can measurably raise top speed while simultaneously lowering the power required to hold that speed. With the airframe and propulsion system optimized, the flight controller becomes the element that decides whether the extra speed remains usable. Its task is to translate pilot stick inputs and gyro data into motor commands with minimal latency and without amplifying noise. Modern firmware includes RPM-based filtering that identifies the exact frequencies produced by each spinning motor and notches them out dynamically. This targeted removal of motor noise leaves the control loop free to respond to genuine flight dynamics rather than mechanical chatter. When filtering is insufficient, high-frequency vibration leaks through, the derivative term overreacts, and the aircraft develops a rapid shake that grows with speed until control is lost. PID tuning then fine-tunes how aggressively and how smoothly those corrections are applied. The proportional gain sets the immediate strength of response to any attitude error. Raising it sharpens cornering and straight-line tracking, but risks overshoot if left unchecked. The derivative gain measures the rate at which the error is changing and applies opposing thrust to damp oscillations. At high speed, this term becomes essential, because momentum turns small errors into large deviations very quickly. The integral gain corrects persistent small offsets caused by minor imbalances or steady wind, yet excessive integral action can produce slow, large amplitude oscillations or integrator windup during sudden throttle changes. The reliable sequence is therefore iterative and data-driven. Establish conservative base values, raise proportional gains axis by axis while performing high-speed straight passes until the first hint of oscillation appears, back the gain off slightly. Then introduce derivative until the oscillation disappears and the aircraft feels planted. Only after each axis is stable are rates increased to unlock faster attitude changes for tighter racing lines. Throughout the process, progressive testing in open space reveals whether the drone still possesses enough thrust margin to recover from disturbances without saturating any motor. Common loss of control events at speed, almost always traced to one of a short list of mechanical or configuration issues, rather than fundamental design limits. An unbalanced or damaged propeller remains the single most frequent cause of high-speed wobble. Rebalancing or replacement restores clean flight immediately. Loose motor mounting screws or a bent motor shaft create periodic thrust variation that the controller interprets as flight error and fights, producing exactly the oscillation the pilot experiences as loss of control. Voltage sag that drops the system below the minimum voltage needed for full ESC operation removes thrust from one or more motors without warning, instantly destroying attitude authority. Insufficient overall thrust-to-weight ratio leaves no reserve for corrections once the drone is already working hard to maintain speed. The remedy is either lighter components or more efficient thrust, never simply more aggressive tuning. Electronic speed controller settings also influence stability under load. Motor timing, startup power, and PWM frequency must be matched to the motor and propeller combination so that commutation remains smooth across the full throttle range. Desynchronization at high RPM produces sudden torque loss on one motor and an immediate yaw or roll that the pilot may not have time to correct. Updating ESC firmware to current versions often improves low-speed smoothness and high-speed reliability without any hardware change. Iterative refinement turns these individual improvements into compounding gains. After any hardware swap or tuning change, the sequence is always the same. Verify basic stability at low throttle with propellers removed or in a safe enclosed area. Progress to gentle maneuvers, then conduct sustained high-speed runs while observing for oscillation, drift, or excessive pilot workload. Onboard logging, when available, exposes frequency content and motor output saturation that visual observation misses. Each cycle of test, analyze, adjust, and retest systematically raises the speed at which the drone remains fully controllable. High-speed operation also accelerates mechanical wear. Bearings, motor shafts, and propeller hubs experience greater forces and heat, periodic inspection for play, unusual noise, or discoloration prevents sudden, mid-flight failure that would otherwise appear as instantaneous loss of control. Propellers should be examined after every hard landing or contact because even small nicks alter balance and aerodynamic efficiency. When all elements, matched propulsion, minimal mass and drag, rigid structure, clean airflow, effective filtering, and properly tuned PID are aligned, speed and control cease to trade off against each other. The aircraft accelerates harder, holds higher velocity with less power, and changes attitude more precisely because every correction benefits from the same efficiency gains that produced the speed in the first place. The pilot experiences a machine that feels planted at velocities that previously produced chaos, because the underlying physics have been engineered rather than overpowered. This methodical elimination of every source of inefficiency and instability is what separates setups that merely go fast from those that go fast while remaining fully under command through the entire racecourse.